Okay. Okay. Well, thank you very much, um, Sasha, and welcome everyone. It's nice to see a lot of people here. I'll just share my screen, uh, and you can all hear me okay? Yeah. Good. All right. So I'm just going to move this onto the other screen. So yeah, Sasha asked me a few months ago just if I could give a sort of practical demonstration of in 3D inversion of some data. So this is a very simplified, going to be a very simplified example, so that the inversions run in real time, but it shows you the sort of process to go through in inverting 3D DC resistivity and IP data in Geoscience ANALYST Pro Geophysics.
Sorry, James. You're showing us it's what you're showing is not presenter mode on your talk. I don't know if that's possible that you put it
Uh,
on presenter mode, or is that intentional
oh yeah,
that you?
yeah. Sorry, no, that's intentional. That's intentional because it goes
Okay.
onto my second screen, which is where my
Oh,
cheat
okay.
notes are.
No, no problem. That's okay.
Yeah, I want to
All
see
right.
my cheat notes. Yeah, okay.
No problem.
Um, so uh, so just a bit of introduction as to what we need to do an inversion. So if I just go to the next slide, we need some data, obviously, which has a normalized potential, or voltage normalized by current, has some sort of chargeability data, and has uncertainties on the potential and the chargeability. We need some topographic data, and we need an Octree mesh for the SimPEG codes. So, and just in case people are not completely familiar with resistivity and IP inversion, it's a two-stage process. You first do the resistivity inversion, and then the resistivity model from that becomes the input, one of the inputs into the inversion for induced polarization. So, just a little bit about the data I'm using here. It's public domain data from a prospect called Beatrice in Western Tasmania, which the data was actually acquired in 1999 by Pasminco Exploration. It's pole-dipole IP with an A of 50 and N goes from 1 to 8. It's frequency domain data acquired using a Zong system, and the IP parameter is 3-point decoupled phase. So, as I said, I got this data from Mineral Resources Tasmania website. I had to do a little bit of reformatting of it to get it into a form where I could get it into ANALYST, but that was mainly just joining, individual lines of data into a single file. I haven't done any other editing of the IP data. It's exactly as I downloaded it. So this is the reference to the report on the MRT website. It's a lovely picture of Western Tasmania in the middle of summer here down the bottom. So um, just to show you what the place looks like, this is just east of Queenstown on the west coast of Tasmania. You're looking down here from the top of Mount Owen across the lovely township of Gormanston. And this survey was acquired on these hills over here in the distance. So very rugged topography, which is why I chose it as the example data set. And, if you've never been to Gormanston, well, you haven't missed much. This is probably one of the best views of it. So just what the data looks like. So, I just downloaded ASCII data from the MRT website. Uh, and this is just a quick snapshot. It's just got a line number, which is the northing, and then coordinates of the four electrodes, so C1, C2, P1, P2, and then apparent resistivity and 3-point decoupled phase. So just a simple column ASCII format. It's a CSV file in this case. So now I'm going to go to Geoscience ANALYST. Um, So I'm using version 4.8.0, which is the current release. It was released a couple of weeks ago. And I'm just starting with a blank project. So the first thing we need to do is bring in our data. So to do that, I go to File, Import, ASCII, and then there's a DCIP option here. And I just select the data file. So I just showed you a screenshot of this data file. You know exactly what it looks like. So it's a CSV file. So if I change the delimiter here to comma, it auto-populates the column titles. And that's because I gave them these particular names. If you call them C1X, C1Y, C1Z, it actually recognizes automatically that that's your first current electrode. So you don't need to go down and assign, 16 different columns of the data file. What I'm going to do before I import it is just ignore the remote and the remote electrode. So the only reason for doing that is just so I can use a smaller mesh and get this inversion to run more quickly for this demo. Such asked me to keep it to around half an hour. So that's the only reason I'm particularly ignoring the remote in this case. So to do that, before we import it, we just go down and set the C2 X, Y, and Z to empty. And then they're just not imported and they're ignored. So once I click OK, we've got a 3D view of the pseudo sections, and I can color, and it's brought the data in as two parts. One part is if these little icons here, one says P and one says C. So one part is just the current electrode position. So if I turn the receivers off, or the potential electrodes off, sorry, one part is just the current electrode positions, and the other part has got the potential electrode information and the pseudo section. So let me just get a better view of that. You can see the lines, and I'm just going to color these pseudo sections by apparent resistivity. So there it is, colored by apparent resistivity. You can have a color bar here if you want. Sorry, there you go. So we've got a resistivity color bar there. I'll just turn the color bar off for a bit of screen real estate. Okay, so the first thing we have to do here for the SimPEG codes, they want to use potential, not or normalized potential, not apparent resistivity for the resistivity inversion. So the first thing we're going to do is just calculate a potential from the apparent resistivity using the geometric information in this survey. So to do that, I'll just right-click on the potential electrode object, go down to DC resistivity options and say calculate apparent resistivity or voltage. And we're calculating voltage from apparent resistivity. So I tick this button here. My apparent resistivity is this field at Bres, and the output name is going to be, I'll just call it V on I, right? It's normalized potential. And I'll click OK. I'll just show you what it looks like. Not as in, it's not a very good color bar here, but it's different data to the apparent resistivity, just to show you it's different. So the next thing I'm going to do is bring in a DEM, and this is some of the pre-processing I did. This survey is obviously in local coordinates. You probably saw that in the preview of the ASCII file. So I have also rotated the DEM, which was in UTMs, into the local coordinate system. I've just done that ahead of time just to save a bit of time. So to import the DEM, it's just a grid. It's just a TIFF. I'm just going to drag and drop that into the viewport, and it imports two objects. One is an image, which you're seeing here in grayscale, and the other is an actual grid. So I'll just turn the grid on. I'll just minimize this thing and just show you that I'll color it by elevation. So, we've got this DEM grid, and you can work with a grid, but it's often nice to work with a DEM surface, or it's easier to work with a surface. So to create a surface from this grid, we just right click on it, say create, and then surface from data. And the property I'm going to create the surface from is the elevation in meters, and I'm going to call it DEM. And it's an old habit of mine, but I've got an underscore TS there. That just means triangulated surface. So if I do that, the 3D surface is generated very quickly. So I'll just turn the grid off. So now, oops, and if you don't like the yellow highlights, you just click on the nodes tab down here and they go away. So we've got our DEM here, DEM surface here, and you can see our pseudo sections that we imported sitting underneath them. So the next step is to drape the pseudo sections under the topography. And to do that, we just select the two. I'll just expand this so you can read what they are. One is the potential, one is the current. We just select both those objects and right click and say drape on. And I can choose an object to drape them on by using this picker tool here. So if I click that and then click on the surface, it will choose that DEM surface, and I've got a vertical offset of 0, so it'll be right underneath DEM. And then I click that, and you'll see that those pseudo sections have moved up and are now draped on topography. Okay, so in the old way of doing DC resistivity and IP inversions, you had to define a topography file, and there's a lot of mucking around. All that is a thing of the past. With this software, it's really easy to get the topographic information on your data, just the way I've shown. So before I continue, I'm just going to save. It's just a good habit in, I'll just call it demo. You can see I've had a few previous attempts here. It's just a good habit in the event of anything untoward happening to your project. So, so the next thing, so we've got some data here. The next thing we need to do is assign some uncertainties to the data. And I just want to choose the potential object, which is the top one here. And if I right click on it and say create, we've got this option of data uncertainty. And I'm going to do the apparent, potential first. So I've got this one called V on I down here. And I'm going to, the uncertainty is going to be 5% of the data plus a floor of 1 millivolt. So these units are volts. So I'm just going to use 1 millivolt. That's a pretty typical choice for, potential data. You could go a bit lower with the floor, but this is what I've used so far. I'm going to stick with it. So I like to name these with, what uncertainties were assigned. So I know, which one I'm dealing with. Sometimes you have to do a bit of experimentation normally when you start out to get the best uncertainty settings for your inversion. I've done that all ahead of time here. So I'll say okay, and we've created an uncertainty property on this for the potential on this data set here. So I'll do the same thing now for the phase for the IP parameter. So data uncertainty, and I'll choose the 3-point decoupled phase, and I'm going to just choose 5%, and it's come up with a default value here of 1.01 for the floor. That's 10% of the standard deviation for the entire data set. And it turns out that's quite a reasonable choice for this data. So if you click that light bulb, that's what that number is. It's just, and you can see that in the data colors thing here. You can see the standard deviation of the entire data set is 1.08, right? Oh, sorry, is that right? Oh, anyway, might have confused myself there. But anyway, this is a good choice of the uncertainty. So I'll just say sorry, PC5 floor. Okay. So now we've created an uncertainty property on the phase there. Okay. So the next thing, so now we've got one of the things we needed, which was data with uncertainties attached. And the next thing we need is to create a mesh for the inversion. And the first thing we need to do to create the mesh is just to create a point set of all the electrode positions, which is just something you need to create the mesh. So to do that, I just select the two objects here, right click, say create points from nodes, and that creates a new point set, which I'm going to call combined. So just the combined current and potential electrode positions. It's just points with they don't have any properties on them. They're just points. I'll just turn the DEM off for you for a second. That's that combined point set that we just made. So it's all the current and potential electrode positions. And the only thing we use this for is to create the Octree mesh. So to create the mesh, we just go to the geophysics menu, and you've got this SimPEG menu, and there's an Octree mesh designer here. So I'll just expand this window before I do anything. To define the actual size of the mesh or the extent of the main part of the mesh, we need this core hull extent. That's that point set that we just made. Okay. And I'm just going to leave, it's got default values are shown in grey here. I'm just going to leave the default at 500 meters for the depth of the mesh. That's fine. For the core cell size of the mesh for DC resistivity and IP, that can't be any bigger than half the A spacing of the survey or the electrode spacing of the survey. So I'm going to use 25 meters. So the A spacing was 50 meters in this case. I'm going to use 25 meters just to make the models run quickly. So normally I would use a quarter of the A spacing or maybe even smaller. So likewise with the padding, normally you would have a bit of padding around the edges of the mesh. In this case, I'm just going to remove or reduce the horizontal padding to 500 meters. Again, this is just to make the mesh a bit smaller and make it run fast. So we've got two other things here. I'll just leave the vertical padding at default. We've got two other things here. We've got diagonal balance, which is ticked on by default. And we've got the minimum refinement level of the Octree mesh. So in the Octree mesh, you start off with a core cell size. In this case, it's 25 meters. And every level of Octree you go up, that cell size doubles. So the core size is 25 meters. The next level is 50 meters. The next level is 100. The next level is 200. So in this mesh, we've got an Octree level of 4. So our maximum cell size in the mesh is going to be 200 by 200 by 200 meters. Okay. And the diagonal balance, all that does is it stops the in the mesh, if two cells share a common node, then those two cells can only be one Octree level apart. So if one is Octree level 2, the one sharing the same node can only be Octree level 3. Right? It can't jump 2 levels of Octree from one cell to another. And I think I can show you that in this demo here, just to show you. This would be an Octree mesh without the diagonal balance turned on. So you've got the core cell size here, and you're jumping to a cell here that's 4 times bigger than this one, or sorry, 8 times bigger than this one by looks. No, 4 times. And then this is a balance mesh where you only go up 1 Octree level as you go from here to here, right? So that's all it means. And it's on by default, so that's the right thing to have on. So that's the first bunch of settings, and then we go into the advanced parameters, and this is where we refine the mesh. And this adds the refinements add detail to the mesh where you need it for the calculation. So those sort of things are around the electrode positions, around the topography, and maybe in the core area of the mesh is where we want the fine detail of the mesh to be. So I'll just turn these on one by one. Refinement A, so this will be adding detail around the electrodes. And I choose that combined transmitter and receiver points set that we created before. And for levels, I'm just going to put 333. Okay, what that means is you're going to get around each electrode position, you're going to get three concentric shells of the smallest Octree mesh size, then three concentric shells of the next cell size, and then three of the next cell size. So that's how you read this stuff. So around each electrode, you'll be getting these shells of electrodes that increase in size as you get away from the electrode position. So refinement B, I'll turn on. In this case, we'll use the topography. So we're going to add some extra detail around the topographic surface. And this is going to be adding, if our first Octree level is 25, it's going to be adding two cells of size 100 around the topography. And I'm just doing it this way to make the mesh small. Okay, so normally you'd add a bit more detail around the topography. So the last refinement here is the just adding a bit more detail in the core of the mesh. And to do that, again, we use the combined transmitter and receiver points. And for levels, I'll do something like 6, 2, 2. And I'll tick on this user's horizon and give it a distance. So what this will do is underneath the core area of the mesh, which is defined by these points here that you can see in the viewer, we'll be adding layers of extra cells. So we'll be adding 6 layers of size 25 meters, and then 2 layers of size 50 and 2 layers of size 100. So this isn't necessarily it's definitely not what I would do in practice. I'd probably add a bit more, even more small cells in the core of the mesh. But what this does is adds some extra fine detail beneath your electrode positions in layers beneath those electrode locations. So it's important there when you use this refinement to turn on this user's horizon, if that's what you want to do. And when you go to, so we're ready to create the mesh. If you click OK or Apply, it will just run the Octree mesh creator and close this window. So a better thing to do is to click this folder in the top bottom left here, and that will create a node in the tree here with Octree Mesh Designer. So before I do anything else, I'm just going to save. And all these SimPEG things work the same way. When you've got a node for whatever it is, the Octree Mesh Designer or the inversion, the various inversions, you just right click on it, and you can either edit the options that are going to be used, or run the action locally. So I'm just going to run this here and give it a name. And this is going to pop up a terminal window. So this SimPEG is all open source and all written in Python. So and Geoscience Analyst Pro Geophysics just provides the interface, a nice graphical interface with all these Python scripts. So you see that took a little while to get started. It takes a few seconds to sort of wind up, and then when it actually runs, it runs very quickly. So we've created the Octree mesh. I'll just close that window. Right click on the Octree Mesh Designer, and now I have the option to load results. So if I load that mesh, it's shown here. Just bear with me. And then I'll just show you what this looks like. So um, you can see here I've got the Octree mesh selected in the tree over here on the left, and I can turn off various, I can manipulate the 3D view with the visual parameters window, which I've got docked here next to the viewport. So if I just turn off a couple of sections here, and I'll just jump to section 28, I think it is, which is pretty close to maybe it's 27, pretty close to this line of electrodes here. So I'm going to just look to the north. So we're looking perfectly north. So at the moment, I'm just going to turn on the grid so you can see the mesh. So this is just an east-west section through the Octree mesh, just showing, here are your electrodes sitting on topography, and you can see, we've got a whole bunch of fine core cells around those electrode locations, and they get progressively, the cells get progressively coarser as you go out towards the edges of the mesh. And if I just turn on, I could quickly show you the DEM. There's the DEM there. You can see that we've got, a little bit of extra, hopefully we've got a little bit of extra detail around the DEM. So that is looking in, we're just looking north there. You can see, well, that's what the Octree mesh looks like. I'll just also show you just a Z section, just so a horizontal plane through the mesh, just to show you what it looks like. And this is at I'm not exactly sure what level this is at, but you can see you've got a mixture of fine and coarse cells as you look at this level through the mesh. But you've got to remember that there's quite a bit of topography on this data set. So these cells here that are very fine would be up closer to the topography than these ones here. So the mesh is, you can have cells of different dimensions all over the place in the mesh. So I will just show you down here, you get some information about the mesh. Some metadata, if I just scroll down in here. So this mesh, has got 31,581 cells. So that's a pretty small mesh. If you had to make a normal UBC style mesh, tensor mesh for this data set, it would be way, way bigger than that. It would take, a lot longer to run. So that's one nice thing about all these SimPEG codes. They all use these Octree meshes, which are very, very efficient. So now we've got two of the things we needed. We've got our data plus uncertainties, and we've got some topography, and we've got a mesh. So we're ready to do an inversion. And I go back to the geophysics menu here to SimPEG, and then under inversion, you can see we've got a great big list of different codes. So Geoscience ANALYST provides interfaces to all these codes. So when you have Pro Geophysics, you get interfaces to all, a lot of different 3D modeling capability. I'm just going to choose direct current 3D here, and I'll stretch this out. Sorry. So we'll just quickly set the parameters. So the object is the data that we imported. The data we're going to use is the normalized potential. The uncertainty, you can either put in a number, you could just type in a number in this box, or if you click this pi symbol here, you can choose a field from that object. So we've got this VI uncertainty. So that's defined the data plus uncertainties that we're going to use. For the mesh, we're going to use that Octree mesh. You can define things either in conductivity or resistivity. I personally like conductivity. Some people are more backward. So you've got a choice of resistivity there. So for the initial resistivity here, I'm going to use 3,000 ohm meters. It's quite a resistive area. So, or 0.0003 Siemens per meter. And I'll use the same value as the reference model. Um, okay, so for the resistivity inversion, we don't need to apply bounds there. We don't need like positivity bounds or anything like that. They're already there. The topography, I just choose that surface that I made. So that's the sort of initial setup there. We go to the advanced parameters, and I'm just going to tone down the influence of the reference model here and put a reference weight of 0.01. So that will sort of de-weight the influence of the reference model on the in the objective function. And I'm going to apply a Z smoothness here of 3, which will tend to make things a bit more vertical in the output. So there are a lot of options here. I'll just stretch this out a bit further. And you know, these are, if you're familiar with the UBC inversions, these are pretty similar to the UBC style, and there's a lot of documentation online about the SimPEG inversions and what these various parameters are. So one thing I'm just going to turn off to make it run more quickly is the IRLS, which is iteratively reweighted least squares. That once you fit your data with your normal L2 inversion, the IRLS just tries to make a more compact model. So just in the interest of speed, I'm just going to put 0 iterations for that. And you know, there are default values for all these things, and you can't necessarily just accept the defaults and expect everything to work. And one of those things that does need to be changed here is the initial beta ratio. We have to reduce that in this case to 1. So the default value of 100 is not a particularly good choice. Resistivity is a nonlinear problem, so we want a couple of iterations of the inversion per beta. And I'm just going to turn these number of iterations down so that just so that it runs more quickly. And I'm going to use a sensitivity a threshold for the sensitivity weights directive of 0.1. So we've now set all these parameters for the inversion. I click OK, and that creates a DC inversion node in the tree here. Before I go anywhere further, I'm just going to save this. So like with the Octree Mesh Designer, I can now right-click on that DC node and either edit the options or run the inversion locally, which is what we want to do. So I'm going to run this. I'll call it so again, this takes a little while to get started, but this inversion only takes about a minute to run. It's probably the longest minute of your life when you're giving a presentation because it seems to take forever. But so what we're seeing here is that we've got a target misfit equal to the number of data points. So 678 is our target misfit. And you can see here you've got the beta value and then the data misfit or the data norm and the model norm here. So you can see that the data norm is decreasing as we, you know, or more or less, it doesn't have to monotonically decrease, but it more or less monotonically decreases with each iteration. So I'm just going to let this run. So, you know, good time to get a cup of tea or something if you're very, very quick, because it will be finished in 20 seconds or so. So you can see this, we're starting to get, you know, pretty close to our target here already. Okay, so that's finished. That was 1 minute and 9 seconds. Felt like a lot longer. So that's just the terminal output of the inversion, you know, running in Python and SimPEG. So now I've run it, I can load the results. So just right-click on the node and load the. Well, what I'll do first, sorry, I'll show you the convergence curves. this just shows you how the data norm and the data misfit and the model misfit are behaving with each iteration, and it looks a bit funny now. I'll just put it in on a log scale, and this is the data misfit. So it starts high and decreases, and the model misfit starts low and increases. This is the way it should look. It looks a bit weird here because we've got 2 iterations per beta, so it looks like little segments for each new beta. So that's just a good idea, to check on how your inversion went. Just have a quick look at that, and then I'm going to load the results. So here, so this has brought in a whole lot of stuff underneath this DC inversion node. So I'll turn off the Octree Mesh Designer and the original data, and I'll just turn off the Octree Mesh for a minute here, and I'll just show you that we are actually fitting the data. So, inside that inversion node, it's brought in the observed and calculated responses. I'll show you the potential data. So at each iteration, you've got the calculated potential, calculated apparent resistivity, and the residual between the calculated potential and observed potential. So you get that information for each iteration of the inversion. So we ran for 13 iterations here. So if I just click on these things here, I'm just going to show you, it's a bit confusing to see all the lines together in 3D, but you can view just one line at a time here. So if I just tick on this lines button here in the visual parameters for that object, just turn them all off, and I'll just turn on the center line. And I'll do the same thing with the current electrode positions. So we just want the center line. Okay, so now I'm going to look north. There's my pseudo section, and I'm just going to make the nodes a little bit bigger so we can see, these nodes a little bit bigger so we can see them. Right? Where's that one gone to? Yeah. So I've just increased the size of the points there. So we can look firstly at the observed apparent resistivity. I'll just turn that on. So that's what that looks like. I'll just set the color range here. So we need to be looking at the same color range for the observed and calculated. So I'm just going to actually set it. If I use a log scaling for the resistivity here, so I've just turned on this lin log button here, and then I'm going to use a logarithmic color stretch. And I'll go from, say, 500 ohm meters to 6,000. And we'll just go back to the viewport. And that's our observed pseudo section. And if we just go to the last iteration of our inversion, it'll look different to start with because I've just got to set the color bar to be the same as the other one. So again, just click the lin logarithmic color stretch, 500 to 6,000. Okay, and now that's our calculated data, calculated apparent resistivity for this line, and this is the observed data. Okay, so they're very, very slightly different. You can see a few changes up near the top of the pseudo section. So we're fitting the data pretty well, and it's the same for the other 2 lines, which I don't have time to show you. So we've done the resistivity inversion, and we'll just quickly do the IP inversion. I'm just going to save. We go to geophysics, SimPEG inversion, and then there's IP 3D inversion down here. So very similar setup to the resistivity inversion. Our object is the same data that we used before, but we're going to use the chargeability data. So the 3-point phase, our uncertainty is that uncertainty we created on the phase data. The mesh now, we don't want to choose the original Octree mesh we made. We want to choose the one output by the 3D resistivity inversion because we need that resistivity model that we got from the resistivity inversion. So I've chosen that second Octree mesh. You can see that it was named Oh, sorry, I actually haven't shown you the output of the inversion result, which I might just quickly do. Sorry, I just realised I showed you the misfit. I didn't show you the model. Uh, Let me just turn these two things off, and we'll just turn the mesh on, um, and I'll just look north. Which is that one? So we're just looking at the Octree mesh here from the resistivity inversion. I'll just turn on a couple of sections. So I think we just need the V section. And I'll just turn the grid off, and I'll turn the last resistivity model on. So this is uh, the the resistivity shown here that's come out of the DC resistivity inversion. And I'll just give it a better color stretch. So we'll go lin log, we'll do a logarithmic color stretch, and I'll do, say, 1 by 10 to the minus 4 to 0.02, say. Um, these are conductivities in Siemens per meters. And then there's a sort of cross section through the inversion result. And if I just turn the Z section on, you can see the resistivity model there. Okay. So I'll just show you where the data was. There's the lines of resistivity data. Okay, so that's our resistivity model that we got from the inversion. So now I'll just finish with the IP inversion. So we want to choose we've chosen this Octree mesh that was output by the inversion. So that's this one under the DC resistivity node here, this one here. The conductivity is we'll choose that last iteration. The initial chargeability, I'll just put it 1 millirad. The reference chargeability, I'll turn on and make it 0. And you do need to apply bounds in here, so I'll just put on a lower bound of 0. In this case, just stops the chargeabilities going negative, unless the observed data is negative, in which case it will fit them. So I'll just choose the topography surface for the topography. And in the inversion parameters, I'm going to use pretty much what I used for the resistivity: a reference weight of 0.1, a Z smoothness of 3, no IRLS, an initial beta of 1. In this case, because the IP inversion is linear, we only need 1 iteration per beta. I'll go down to 20 iterations here and 15 here. Okay, so I think pretty much this is exactly what I chose for the resistivity inversion, apart from this iterations per beta here. And then this was 0.1. The threshold here was 0.1. So I'll just say OK, and that's created this IP inversion node here. I'm just going to call me paranoid, but I'm just going to save. And then, just as we did with the resistivity inversion, we can right-click on this and run local and call it IP demo. And this is extremely similar to the resistivity inversion. Again, this takes about a minute and feels like an hour. So we've got the same target misfit, which is just equal to the number of data. So your beta value here, your data misfit, model misfit. So you can see that we're improving the data misfit already. I'll just wait for this to run. Talk amongst yourselves. Just have a sip of coffee. It's like watching grass grow, but anyway. So we're starting to get pretty close now. Okay, so that was, took just about as long as the resistivity inversion. I'll close that. And I can do the same things. If I right click on the IP inversion node, I can view the convergence curves, and they look, this is the way they normally look. The data misfit starts high and goes low, and the model misfit starts low and goes high. So this looks normal. And you can uh, load the results here. So I'll just turn the resistivity stuff off. So again, we're just looking at the output from the IP inversion. I'll just turn the model off for a second and again just show you that we're fitting the data. So I'll just turn on that center line on both of these. And we just look at the observed chargeability, which is this, and I can make these numbers a bit bigger, that make these points a bit bigger. So this is our observed chargeability, and this is the chargeability from the last iteration. So they're already on the same color bar, and they're very, very similar, right? You can see very slight differences between them. So we're fitting the data pretty well. So I'll turn that off and just show you the model. So the model here, if I show you the parameters on the model, you've got the conductivity model that you used, which was our 13th iteration from the resistivity inversion, and then the eight iterations of the IP inversion. So I'll just turn the last one on. So there's like a 3D view of our IP, of our chargeability model. Okay. And I'll just turn the color bar on. So we're sort of going from 0 to 70 roughly milliradians here in the model. So these results that I got out of these inversions were pretty similar to the inversions that were done at the time by Pasmingo. So in terms of, distribution and magnitude of resistivity and chargeability. So the last thing we can do here is we've got the whole mesh here. So if I turned on the mesh of this model, turn on the grid, you'll see we've got the whole Octree here with all the padding cells and everything. And we just want to cut that down to the core of the mesh. So I'm just going to show the current electrode location. So I've got something to refer to, and I'll just turn the mesh off again. But, and sorry, I have to show all the lines here. So there's 3 survey lines. I just want to clip the mesh down to the area of the actual measurements. And to do that, I just choose the mesh in the tree here and right click, and I can say create block model from core volume. And that'll bring up this box here. And I'm just going to, oh, sorry, I keep bumping the mouse. I'll just view it in from above. So we're just looking down in plan on the mesh, and you can use these sliders here to define the clip limits for the mesh, right? So I'm just going to basically trim in X and Y the extents of the mesh. And then we can look north here and also trim in Z. So I'll just come up to, I don't know, somewhere about here. And maybe here the topography might be different on different lines. So you can choose which, properties to transfer to the block model. We don't have to have everything. We can turn everything off and just have the conductivity model and the final inversion of the IP, right? And I'll click back here. And then we just say OK. And this will create a new object in here called extracted core, which is just that core part of the mesh corresponding to the, where the data was. So you can see that sort of verticality of that body by putting that Z smoothness of 3 in the inversion there. So we're looking here at that's the IP model, that's the chargeability model, and this is the resistivity model. Okay. So and once you've got it as a voxet like that, you can or a voxel model, so that if I turn on the mesh of this thing, I'll just show you the grid. This has just got a regular cell size. Okay. I'll just turn off. So it's just every cell is exactly the same size in this model. So once you've got something like that, you can do the normal sort of things you might do for any block model. We have the option here to make isosurfaces and that sort of thing. So, I mean, I can do that. At the risk of going off script, there's a chargeability isosurface at 30 milliradians. Okay. So, and that can be exported as a surface that can then be exported as DXF from here. So likewise, once we've got this, once we've extracted the core from the Octree mesh, we can right-click on the core here in the tree and say export, and you have the option to export that as a UBC mesh and model file. Okay. All right. So there it is in a nutshell. It was a bit longer than 30 minutes, but I guess I'm about to find out if any of you have stayed with me. So,
thanks very much, James. That
no
was
problems.
great. This has been our most popular, I think, seminar so far in terms of the number of participants. So thank you. And there are, I guess, a few questions online. I'll go through them. We have another 5 minutes to the end of basically an hour. Januko asks, how do you set the target misfit and what is it based on?
Oh, so the target it's very, these UBC style inversions all work the same way. The target chi-squared misfit will be equal to the number of data. So if you have that misfit level of, is that what the question is about,
I
or
think
is it
you
about
don't set it,
setting the
right? It
uncertainties?
does. Yeah.
Oh, well, you can set it, you can change it. So you can,
Yeah.
normally it's 1, which means that your target
Yeah.
misfit is equal to the number of data points, number of observations. But if you can try and overfit the inversion, so you can set it at 0.5 or 0.1 and drive the inversion past, to the point where you're, potentially fitting noise in the data. You're sort of overfitting the data. And then in that case, when you do that, the reason is to make sure you're really, really fitting your data well, and you wouldn't use the last iteration. In that case, you would go back a few iterations to where, you're fitting the data well, but you're not you're not seeing artifacts related to fitting noise in the data. So it's quite subjective. Yeah.
Yep.
Yeah.
There's another one. Can 2D ERT data be fed to geoscience analysts to get 3D models, or it should be in 3D data mode only?
So this was really a bunch of 2D lines. So I would say yes, you can. You've got to get it in a format where analysts can recognize it as 3D data set. So
most of the time
yeah.
that's the case.
So I didn't run the I didn't run the I didn't run it in 2D mode this time, but we are running this as a demonstration at the Discover conference coming up in Cairns. So and at Saga. So if you are interested in seeing the 2D inversion part,
Yeah.
and you're going to either of those two conferences,
Mm.
we will be going through the 2D inversion as well.
There's another question from Robert Cromet. I said, can you clip mesh based on sensitivity or other DOI metrics?
Uh, yeah, you can. I can't remember whether
Does it calculate this DOI itself, or do you need to
it
rerun the
doesn't calculate
inversions
it
with
itself.
some primary,
It's got a
like
C if
initial
I.
models difference? Is that what you do? Two different initial models and then you clip them?
Yeah, you can do it.
Mm.
You can do it that way. Just checking. Oh yeah, see, I didn't turn it on here, but
Yeah.
you can export the sensitivities
Uh-huh.
here, and then you can clip by sensitivity. Yeah.
Okay.
So but you have to actually tick this on. I just didn't do it in this demo. So
Yeah.
yeah, I mean it's a pretty good interface for the 3D inversion. It does most of the things people normally want to do. So maybe in the Discover conference and Saga we'll add this.
Mm. Mm.
We'll demonstrate this option.
Mm-hmm.
Yeah.
How can I convert my field data to compatible data for making inversion?
Well, basically that data format is very conventional and very straightforward.
Mm.
It's just a line number and the
Mm-hmm.
coordinates of the four electrodes and
Mm-hmm.
your apparent resistivity and chargeability. So the data that I downloaded from MRT wasn't exactly in this format. I
Yep.
did do a little bit of manual editing to get it. I just got rid of all the columns I didn't really need.
Yep.
But it's pretty straightforward. I mean,
Yep.
Excel or a text editor will do it, and or other third party software like TQIP, uh, can export data in this kind of
Yep.
format that can go straight into Geoscience Analyst.
All right. I guess we are finishing on time, which is great. Thanks, James. And
No
you will
problems.
present this a more extended version in Cairns this year, right? At the end of the year for ACG Discover. Is that what
Yeah,
you have a
and
workshop
Saga
and
and
Saga
Saga.
and Saga?
Mm, mm.
And I guess this is recorded, everybody, and we will have it online in ACG website, and we will send you a link to the video when it's downloaded,
Yeah,
uploaded, and maybe I ask you, James, do you give the registration of your workshop so we can put it in the email, send it to participants if they are interested to know more about it.
yeah.
They can, if they attend, at least they can take their time and ask questions.
Yeah.
Um,
So at Discover, the workshops are all free to register. So you
yes, that's
just
right.
basically
Yep,
have to
yep.
basically to say
Register.
you're coming. Yeah,
Yep,
yeah.
yeah. Register
When
for
you
the
register for the
conference. That
conference. Yeah.
and it is in September, right? ACG Discover, is
Uh,
it? Or no, no,
October, end of October.
October.
Mm,
Yeah,
mm.
awesome. That would be great. I'm very
Yeah,
excited about ACG Discover, and I found the free workshops were really the best last year, like last time. It works really well.
yeah.
Yeah,
Everyone liked it. Everyone liked
yeah.
it.
All right,
So
thanks everybody. Yeah, sorry, go
yeah,
ahead, James.
thank you, everyone. I was just going to say thank you, everyone, for attending. It's nice to see
Yeah,
a bit of interest.
yeah, absolutely.
And feel free to contact me or anyone else at Mira. If you've got specific
Yeah.
questions about the software or
Mm,
particular data set, we
mm.
can help you out. Okay,
All right.
thank you.
Thanks, everybody. Thanks, James. I
Cheers.
appreciate it.
Okay,
Have a
no
great day,
worries.
everyone.